Okay, welcome back. Let's continue looking at the penicillin story as we are looking at a very important product called an antibiotic penicillin, a little bit about some of the biological aspects of it and the engineering of the production of penicillin. So we're looking at penicillin. It's an antibacterial drug, and we'll take a little bit look at the engineering of the production of penicillin. Okay, so how do you make penicillin? Not the accidental discovery that Fleming had. How do you actually make? Well, we identify the bug, the mold, and grow them in large quantities, right? We had to, how do you grow them? You had to grow them by providing them the food. So we need to figure out what type of food would these bugs actually need. So we had to figure that out. Then supply them with the food so they will actually grow. And it also turns out that we need to figure out how to force them to make the drug that we want. Because it turns out that penicillin is produced when these bugs are under stress, as it were. So, so how do we stress them so that, because they don't dry, but they actually make the drug and that we can actually recover? How do you stress them? How do you stress them just the right way so that they'll make the drug and also survive? We need to understand that. As I mentioned in the last video, we had to identify the optimal strain. Turns out that there is a strain called Penicillium chrysogenum. There are strains called Penicillium rubens, and so on and so forth. Scientists identified which is a strain that will grow to in large quantities, be the most optimal for recovering penicillin from it. So we got to select the strain that is easy to grow, easy to maintain, and also gives us the largest amount of penicillin for the lowest price. It turns out that penicillin itself is not very difficult to find. You might even see it without even knowing what it is. It's mold. It's something that you would normally reject, throw them away, right? But then that's one thing. But to be able to identify something that you're going to use to manufacture is a different story. And here are some links that you may have to follow up about penicillium on cheese, for example. You can take a look at it. Okay, one of the objectives, the engineer's objective, is to make penicillin, the antibiotic, in sufficient quantities for the demand that is expected in the marketplace. We need to make enough. I mean, let's say we need to supply enough penicillin for, say, 10 million people or 50 million people. You need to have an approximate idea as how much it'll need per person, per incident, and how to make it for the 50 million people that it might be needed for. So that's an important variable we need to study. Economics, it needs to be reasonable and affordable. If the price of the drug it's so expensive that only few people in the world can afford it, then it's not going to be manufactured in large quantities. And so one of the beauties about the engineering is, of course, initially it might be expensive, but over time, as the methods get better, the price actually falls. So today, for example, antibiotics and so forth are so inexpensive, we don't think about the prices that much because it is affordable. And it's all certainly a bunch of clever engineering has gone into producing these drugs. Certainly, safety is a very important part of it. The engineer has to design a process that is safe, package it, and be able ready to transport it. Okay, so very, very briefly, what are some of the engineering criteria, engineering factors that somebody might be looking at? So, for example, as far as the engineering is concerned, some of the factors are things like conversions and yields. How much of the penicillin is made at a given unit of time per some unit of the mold, for example? What type of raw materials do we need? What type of equipment might we need to process those raw materials? What type of utilities we might need? Because these things typically run 24/7, 365. What type of utilities do we need and so forth? What type of labor do we need? Do we need somebody watching the reactor all the time? So those are the sort of issues that the engineer considers in terms of designing the process, trying to calculate what it will actually cost to purchase equipment, install the equipment, actually run the plant. So these are all important engineering criteria, engineering factors, if you will. So for most chemicals, and most this includes biochemicals, you can divide the process into two: production and purification. So, for example, for penicillin, the production process is when you combine raw materials, utilities, labor, so on and so forth, into making the product. And then the second step, if you will, is the processing or the purification step, where you might still need consumables, where you're going to purify your chemical of interest from a large amount of other chemicals, including water, and into a final product. So this is a simplified diagram of what a production process might look for, say, a chemical like penicillin. So again, process production: you grow, select strain, design the medium, allow them to grow, you stress the culture, if you will, make penicillin, and you recover the penicillin. There are, as I mentioned, the other issues involved are things like sterilization. We need to remember penicillin, we are growing this in a very rich medium where we are encouraging the penicillin mold to grow. So you can imagine lots of other bacteria and mold in the environment might love to be in there to chew up the food. So we need to make sure that the environment is protected for the penicillin only, Chrysogenum or penicillin strain only, for it to grow. So it's a non-trivial process, but engineers have perfected that method, and we're able to grow them safely and at a price that we can actually afford. In the purification step, we are always faced with challenges. So, for example, penicillin itself is a soluble chemical in the medium. So one of the steps, so the engineer has to ask, how do I separate a soluble chemical from large amounts of water, cell debris, lots of other things in the fermentation vat, right? So he or she has to consider different ways. How do you recover the particles? How do you recover soluble components? So on and so forth. So there are a number of these different decisions have to be made before you design the process to achieve the objective. The extraction of the penicillin is probably the hardest of all the steps in the process. And it turns out that a key development in World War II was a refining of a method called liquid-liquid extraction. So you take an aqueous solution that contains penicillin and you mix it with a non-aqueous solution or some other type of aqueous solution that does not contain penicillin, and penicillin travels from the aqueous medium to the other liquid medium, and then you use that to isolate and purify the penicillin. So this is an amazing technology that was refined and developed in World War II. And then, of course, it has to be dried and packaged and so forth. So our objective is to get the drug in the pure form as possible. And here's some diagram about how you might be able to use two different phases to do the extraction. And here is some a centrifugal extractor. This is just an example. There are a number of these commercially available liquid extraction units that one could purchase for doing these type of extractions. The important lesson here is liquid extraction as a means to do large-scale separation purification was first came on board, if you will, during the penicillin crisis days, where we had to extract penicillin in large quantities from large amounts of water-based systems. And this is just don't even worry about the details in this diagram, but here is a diagram, process flow diagram as it is called, about penicillin production. And you can find examples of this. This is actually from a software package called SuperPro, which is a commercial software package. Our students actually use it for doing some simulations as part of their undergraduate design projects. And this actually shows all the different steps involved in the making of the penicillin, from mixing, from reaction, from liquid extraction, from filtration, so on and so forth. So the engineer essentially assembles this process using individual units and connects them in different ways to achieve the objective.